Welcome to this lecture in module 2. This lecture is on combinational circuit design considering variations. So, we will first discuss inverse narrow width effect, and considering inverse narrow width effect, how we do circuit design, and then we will discuss process induced mechanical stress and how that can be considered in circuit design, and then we will discuss an example of buffer design and a decoder design for discussing this variation aware circuit design methods. Variations are in general of two types: variability. So, one is random variability, which is modeled in statistical manner as a, for example, the mean value of on current, and then there is a standard deviation for the on currents variation. So, it is assumed as a Gaussian distribution, for example. So this is a complete random variation, which can be because of random dopant fluctuations or line edge roughness, such random device or process level effects. Then there are also systematic variations. So, systematic variations are, as we will see examples, they are variations which can be modeled with respect to layout level parameters or device level parameters. Now, these systematic variations, can they be taken into the circuit design methods? For example, we have had this effective current model derivation for suppose an AND gate. Then can the systematic variations be taken into account and the effective current value be modified accordingly and taken into design considerations a priori? So, that is the approach that we will be following in today's lecture. So, in these days with shallow trench isolation based technology, so each device is isolated by a shallow trench isolation which surrounds the device from all the sides: source, drain and gate. For example, if this is the simple concept diagram of a layout of a device, this is the device, this is gate, source, drain, then shallow trench isolation you will find to be present all around the device. We will have shallow trench isolation. Okay. Now, this is around, say, much deeper than the source drain, okay, and surrounds from all the sides. So, it also surrounds from the width side. This is the width, isn't it? And this is the channel length. So, it also surrounds from the width side. So, if you have a cross sectional cut line and look across this cut line, across this cross section, then you will see the length. And if you get along this line and see the cross section like this, then you will see this figure. So, in this figure you are seeing the device from the width side. So, this is the width and this is the length. So, you have cut it from here. So, therefore, this is the width that you are seeing, and the shallow drain, this is source drain contact hole. So, there are these contacts on both the sides, and this is that one of the contact holes which you are seeing here, and shallow trench isolation is surrounding from all the sides. So, what happens is the gate is going over the STI, as you can see in the layout also. So, gate is going over the STI and this is the gate, and therefore, there is fringing electric field from the gate into the depletion region here. So, some of the charges in the depletion region are getting associated with the gate voltage. So, when you increase the gate voltage, the depletion region, some of the charges actually have electric field lines terminating from the gate through the STI. So, these depletion charges are no longer available to the gate charges. So, gate charges would therefore induce more inversion charges if the device is already inverted. So, that would if the gate so that would reduce in effect the threshold voltage. So, that is inverse narrow width effect. Why is it inverse? Because earlier there were narrow width effects which used to in earlier technologies which used to increase threshold voltage, but these technologies with shallow trench isolation, 65 nanometer, 130 nanometer, 180 nanometer, 45 nanometer, all these planar technologies with shallow trench isolation. So, all these devices have inverse narrow width effect. So, when you increase the width of the device, the lesser number of lesser depletion charge is affected by these fringing fields, because the overall depletion charge increases and the fringing fields would affect only the depletion charge very close to the STI. So, therefore, the effect becomes lesser and threshold voltage keeps on increasing. So, when you reduce the width of the device, the threshold voltage keeps on reducing. So, as you can see here, as you reduce the gate voltage, the threshold voltage reduces, and it is fairly linear reduction in the range of our interest, in the range of widths of our interest. We are mostly dealing with standard cell design or standard cells. So, the device width, finger width, so to say, would not be very large. So, you usually use fingered layouts and finger width would be within a certain range depending on the track height of the standard cell library. So, the finger width would be quite small and you would be limited to a very small range of this x axis, and therefore, you would find that the threshold voltage almost reduces linearly as you reduce the width of the device. So, how do we use this in inverse narrow width effect aware circuit design? So, let us look at the inverter. So, we will revisit the discussion on inverter that we had in this course and now try to incorporate our knowledge of inverse narrow width effect into that design methodology. Suppose you have been given a maximum energy consumption per clock cycle per operation which you can bear. So, this is the maximum energy consumption per clock cycle which should happen in your low voltage or near threshold circuit, and you know the logic depth. For the path, you know the maximum energy consumption and you know the logic depth. So, once you know the logic depth, per stage you can estimate this is the maximum energy consumption that should happen. So, how would it, and you are also given you are asked that within that maximum energy consumption, so you should not consume more than that a certain energy per clock cycle. Within that constraint, you maximize the speed. That is the requirement given. Maximize speed for a given maximum energy consumption. So, first step that we would follow is that now you have been given a PDK, and in that PDK physical design kit, that is suppose 65 nanometer CMOS technology of a given foundry, of a certain foundry. So, that foundry gives you a PDK, physical design kit, which includes all device models, interconnect models, etc. So, for this PDK, you extract the slope and intercept of the change in threshold voltage with respect to the device width for both PMOS and NMOS devices. Suppose you are interested in standard VT technology, standard VT devices of the library. So, library may, the device PDK may have low VT, standard VT, high VT devices of several flavors. Suppose you are interested right now in standard VT devices. So, for SVT device, you will plot threshold voltage versus intercept. So, how would you extract the threshold voltage? So, here I would say that you extract the linear threshold voltage, VTH linear. So, how would you extract that? Keep VD plot ID versus VGS. So, you would get a, suppose you get a curve of this kind, and then, so this is not sub threshold, you are going into the above threshold regime voltages, and keep a VDS equal to 0.05 volts. So, then extend this to the x axis, this you call the threshold voltage. Okay. So, now this threshold voltage you extract for several values of the device width for both PMOS and NMOS separately, and then plot device threshold voltage with respect to width. As you increase the width, the threshold voltage would increase, and the range of width you keep within the range of the track height of the standard cell library that you have. So, every standard cell library has a track height, that would be typically the distance between its supply line and ground line. So, the width, choose widths from W minimum given by the PDK to the track height. Track height of the standard cell library, you will get almost a linear plot. So, that you extract the slope and intercept. Slope and intercept of this. So, once you have done this at the device level, you have for any device width, you have the value of threshold voltage. So, you are considering inverse narrow width effect now. Now, how would we design the inverter cell? So, choose a certain Wn based on other design considerations, the normal design considerations. Okay. So, and there is no fingering, assume that there is no fingering now, it is a single finger device. So, typically choose the maximum value of Wn that you would use as a single finger. So, this Wn, keep it to be maximum value for a single finger in the library. Okay. So, in the standard cell library. Okay. So, now for that Wn, now you choose a WP for which I effective of P MOSFET and I effective of N MOSFET are equal. So, that the transition times would then be rise and fall transition times would be then equal. So, how would you get this? So, you know the threshold voltage from here, and then once you know the threshold voltage, we know how to compute I effective for P MOSFET and for N MOSFET from our previous lecture. So, we will get IL, IH, and these IL, IH are dependent on threshold voltage. So, we know what are their values, and those IL, IH we will use to get effective currents. So, for each bit you have a different IL and IH, and therefore, you have a different effective current. So, as you choose a certain value of Wn and change the value of WP until I effective of P MOSFET matches I effective for N MOSFET. Now, that is the P MOSFET finger width that you have chosen, okay, for single finger layout. So, here you have 3 fingers, but you are doing this for a single finger case. So, then you compute the value of P MOSFET, so called off current, okay, because its VGS is off 0 and VDS is minus VDD, and N MOSFET off current. Okay. Once you get these two, you can get the leakage power when the input of the inverter is 0, and also the leakage power when the input of the inverter is VDD. So, in both the cases you get the leakage currents. Okay. So, after you have gotten these two, then so one of the devices would have the leakage current flowing through it, which you get like this. And for example, if the input is VDD, then this is the leakage current, okay, and this leakage current would flow through the N MOSFET also, it would flow through the N MOSFET also. So, you calculate this and you have the inverter. Suppose input is VDD, then IP leakage is flowing through this, and that would also flow through the N MOSFET. So, the N MOSFET has what is the VDS value. So, you will say that IP leakage is equal to IN, which is I naught exponential VDD, which is VGS, minus VTHN. The voltage at the output node, we are calling it VSS low, okay, and it is quite small. So, we are neglecting DIBL related effects, and body effect is also 0 by NVT into 1 minus exponential VSS low divided by VT, which is thermal voltage. So, now you know IP leakage and that is equal to this I naught. So, that will allow us to calculate VSS low. So, this VSS low, likewise you calculate VDD high, which is the highest output voltage value for the inverter considering the leakage current of N MOSFET, okay, when the input is VDD, when the input is 0. When the input is 0, there is leakage current through the N MOSFET, which is this, and that is equal to the value of IP. So, therefore, the output would not be VDD, but it would be what we call here VDD high. So, it would be that value and that value would be slightly smaller than the power supply voltage VDD and that can similarly be calculated. Now, these two VDD high and VSS low should be within tolerable limits that are given by your specifications. If that does not happen, then you would choose the value of WP and WN accordingly. Suppose VDD high, is lower than what you want it to be higher. So, for it to be higher, you want to reduce the N MOSFET leakage current. So, for that you would increase the value of WP. Okay. So, that would for the same value of the N MOSFET leakage current, you would actually get a larger VDD high. Now, after you have met with your specifications for VDD high and VSS low, now you compute the average leakage power of the inverter for this value of input and these values of input voltage. Why these values? Because the inverter driving our inverter which we are designing would also be similar and it would have the same value of VSS low and VDD high. So, for this now calculate the leakage power. What is this leakage power, average leakage power? This current into VDD and when the input is VDD and when input is 0, this current into VDD, that is the leakage power. And consider that the input is 0 and 1 for logic 1 and logic 0 for almost equal amounts of time, then just take the average of these two currents and multiply it with VDD, that is the average leakage power of the inverter. So, then after this compute the FO4 delay of the inverter using the effective current of the inverter. What is its value? So, its value is half VDD into CL, where CL is FO4 CL, okay, divided by I effective. Okay, so this CL is here FO4 of fan out of 4 load capacitance. So, once you have done that, then compute the dynamic energy. So, take this input capacitance, assuming that a similar, you are suppose driving a similar kind of inverter. So, take this input capacitance and this is the dynamic energy for that a similar inverter load and then this is like a representative and compute the leakage power. So, typical logic depth that you want to consider and FO4 delay would be scaling factor because you are assuming that the clock period would be proportional to FO4 delay of the inverter. So, therefore, this is representative of the clock period. So, you are assuming that this is proportional to the clock period into the leakage power that you had calculated here, average leakage power. So, this is the leakage energy. So, total energy is sum of these two and this is taking into consideration the entire logic path and also there is this representative of clock period. So, this would represent the total energy typical for this total energy for this path. So, now this should be smaller than the specified value. So, once this is done, your single finger device with respect to single finger layout with respect to inverse narrow width effect has been systematically done. Now, we will further optimize the inverter layout. So, what would happen if we increase the number of fingers? If we increase the number of fingers for the same device widths, we would have a smaller threshold voltage. That would increase the leakage energy, leakage currents would increase, but that would also increase the speed of the inverter, the delays would reduce. So, that would in effect also reduce the clock period, and therefore, the overall leakage energy we do not know whether it reduces or increases, there is an optimum there, and that is what we are trying to now use. So, we will increase the number of fingers NF for the design that we have done already. We would increase the number of fingers NF from 1 to 2 and then from 2 to 3, progressively we will keep on increasing. Okay. So, for example, here you have a 3-finger layout shown, but we are now going from 1 to 2. We had 1 finger layout and we are going for 2 fingers. So, finger width would come out to be this, isn't? For the P MOSFET, the finger width come out to be this, okay, WP by 2. Now, with this, the threshold voltage of the N MOSFET and the threshold voltage of P MOSFET would have changed, and that we can obtain from our threshold voltage versus width plot that we have, the slope and intercept there, okay. And using that, we will find out the threshold voltages of P MOSFET and N MOSFET. So, we will again recalculate the effective currents of P MOSFET and N MOSFET, and we will see whether they equate now. They will not equate because they will not be equal now, because the threshold voltages have changed. So, now we will again increase. So, suppose the effective current of P MOSFET is now larger than that of the N MOSFET, suppose. So, in that case, the threshold voltage of P MOSFET needs to be increased. So, what we will do? We will increase the value of WP, not NF, because the layout should have same number of fingers for N MOSFET and P MOSFET, otherwise the layout becomes quite cumbersome. So, we will keep the same number of fingers. So, that is why we will increase now WP. So, once we increase WP, you will find that the threshold voltage of P MOSFET increases, and therefore, effective current of P MOSFET would keep on reducing. It would match that of the N MOSFET effective current, and once it matches, we will stop there. So, we will keep that new WP, okay. So, now for each of the fingers taken separately, we will calculate this leakage current, we will recalculate the leakage currents, okay, and again verify that this VDD high and VSS low are within tolerable limits. Then, because for all the fingers taken together or for each of the fingers, the calculations would come out to be the same for these things. Then, for leakage power of the inverter, you will again do at a finger level, you will see whether the leakage power is within the, what is the value of leakage power. Then you will calculate average leakage power, that is for the P MOSFET input being 0 or input being VDD, and then you would compute FO4 delay from effective current for the new finger width. Once you have done that, you will also calculate the dynamic power. There you will multiply with number of fingers. You have done this at finger level, but you will multiply with number of fingers, because that is the inverter's total dynamic energy. And you have done this FO4 delay is that of the inverter, it is representative of the clock period as earlier. So, you will calculate this leakage current and then the total energy, which is E dynamic plus E leakage. Now, this total energy should be within the constraints that you want. So, this is met, then you will increase NF. If this is met, increase NF. Again redo the calculations, and you will increase the number of fingers till the time this is met. But once for a given number of fingers, the E total is beyond your specified value, then you will not increase NF any further. So, increasing NF reduces the threshold voltage, and therefore, you have maximized speed. So, you have in this way achieved the goal of maximizing speed for a given total energy per cycle specification. So, in this lecture, we have discussed inverse narrow width effect and how inverse narrow width effect can be taken into consideration for near threshold inverter standard cell design. Thank you.